Good afternoon, everybody. Welcome. I'm Phil Duxbury, Dean of the College of Natural Science, and I will be your MC for today's celebration. Thank you for joining us on this important and joyous occasion for the Department of Mathematics, the college, and the entire university community. Before we get too far into the formal part of our program, I would like to take a minute to acknowledge a few individuals in attendance today. First, I am delighted that Dan Van Haften is with us this afternoon. Dan, thanks for being here and for all your contributions to Michigan State. We're looking forward to hearing from you later in the program. I'm also pleased that Dan's longtime friend, fellow MSU alumnus and co-author of several books, David Hirsch, Dan's sister Susan, and an arts and letters alumnus, and brother-in-law Rod, an MSU political science alumnus, could all join us today. It's great to have you here with us as we recognize Francois with this prestigious honor. And of course, a big welcome to Francois' family, colleagues, and lab members in attendance today. Okay, on with the celebration. Our program today will touch on the importance of the Van Haften Endowed Professor in Deductive Literacy designation and the long-term impact that endowed faculty positions have on the continued excellence of the university and the college. Let me personally congratulate Dr. Francois Greer for his outstanding achievements to date, which are recognized by this prestigious endowed professorship. Following a few remarks and a brief introduction about Dr. Greer from Mathematics Chair Jeffrey Schenker, we will hear from our honoree and have his formal investiture. Finally, Dan Van Haften will provide a few remarks about his interesting and compelling journey to establishing the Dan Van Haften Endowed Professor in Deductive Literacy that we are conferring for the first time today. With that, I would like to turn the program over to MSU Provost and Interim President Designate Teresa K. Woodruff.
Thank you very much, Dean Duxbury, and welcome to everyone, our guests, our honorand, and everyone who is here today. It's really a joy and a delight to be part of an inaugural investiture, and for this one, the Van Haften Inaugural Endowed Professorship in Deductive Literacy is just really quite a thrill. It's really been wonderful to be back in all of these investitures, and I don't take that lightly because I've had to invest people at a distance, and so in fact being able to do it in person still is a really important part of what we do. I too want to thank Dan and your family and really acknowledge you for your generosity in what you've done to endow this position, honoring your parents, the late James and Esther Van Haften. And I know from your remarks earlier this year that they set a lifelong example for you and is really why you're doing this today. I was very deeply moved by Dan's remarks at our recent university investiture. It was just a month ago, although it feels like it was a year ago. Anybody in the room feel that way as well? But it really was September 14th, and when I saw that, I thought, Phil, that's not the case. It was much longer ago. But it was here in the Wharton Center, and you were just so incredibly eloquent and heartfelt and really talking about your parents and talking about Abraham Lincoln's passion for geometry and how that rekindled your own passion for geometry. And so I was so inspired, I invited him to my office the next day, and the only time I had open was like 7:30 in the morning, and there you were, right there. And he came and brought to me his book, The Tyranny of Public Discourse, Abraham Lincoln's Six-Element Antidote for Meaningful and Persuasive Writing. And then I went and got The Ultimate Guide to the Declaration of Independence, The Ultimate Guide to the Gettysburg. I have all your books, and I have read them all. Francois, I'm not going to ask you if you have or have not, but let me suggest to the Department of Math that you would be well edified by reading these books. And really, I'm so delighted to meet your co-author, David Hirsch, and really just prismatic thinking in these really eloquent ways of understanding. And I hope you will mark my own remarks today under your own special guide for how these marks should be done. I think that of scholarly philanthropy is something we've talked about. We've talked about different kinds of philanthropy, but I think you're an exemplar of scholarly philanthropy. Those for whom you deeply understand and recognize that investing in scholarship is investing in the heart of what it means to be a scholar, because you recognize the work and you recognize the person. And here today, you're recognizing MSU at a particular moment in time. And your confidence in us, your confidence in natural science, your confidence in Dean Duxbury and his leadership, your confidence that we will continue to lead in scholarly areas in this new area of deductive literacy is really something that I so value. So thank you so very much. So today we are going to play a little catch up with Dr. Greer. He joined us in August of 2021 but has already proved through your research accomplishments in algebraic geometry, which I did look up, so just how fortunate we are, to really have you as part of this community. And I'm really confident that Francois Greer will continue to make significant contributions to your field, and you'll play a strong leadership role at this institution, because that's what we are investing in you, that opportunity to excel in all the ways in which the land-grant ethos calls us to service by new discovery and by teaching that to our students. And I think your students some of your students are here, and I think you mentioned that as well. And so very directly, I have started in the 2 years of investitures I've done, I have given a charge to each of our endowed professors. And so, Dr. Greer, I give you this charge. Endowed professorships are among the highest honors a university bestows. They are given in recognition of the work that has been done and the great expectation of the work yet to come. And so I charge you to not sit in your endowed professorship, but to be stirred to new levels of creativity. Be untethered from conventional thinking and create impact that befits the nature of an endowed professorship and our investment of trust in you and the work. We are grateful for endowed funds, which strengthen our ability to grow and nurture the areas of scholarship and research to which they are committed, and we charge you with these acts. So when people look at Michigan State University, what do they see? They see something powerful. They see each of you. And it is that continued striving for excellence in all we do that we have to recommit ourselves to. Because indeed we make a difference. So today we celebrate adding a layer of stability, not instability, to this institution and to excellence as we confer the Van Haften Endowed Professorship in Deductive Literacy to Dr. Greer. Congratulations very much.
So I think we're going to do the medaling now, is that right? Is that the plan?
Dr. Greer.
Thank you, Dr. Woodruff. Again, Francois, on behalf of the College of Natural Science, congratulations on this well-deserved honor. Named faculty chairs and professorships are very important for both the individual and the university, and are critical to increasing Michigan State's competitiveness nationally and internationally. Endowed faculty positions provide the long-term stability needed for serious and significant scientific advancement, freeing the endowed faculty and their research programs from the shortened time horizons and politically constrained financial environment that we live in. These professorships are awarded to only the most outstanding faculty in the university and are meant to recognize exceptional leadership and research productivity. The bestowing of this professorship to Dr. Greer will help guarantee Michigan State's continued capacity to enhance its national and international reputation in algebraic geometry and ensure that students receive rigorous and rich classroom experiences around topics in this important and growing field. The impact of these types of endowed position is much broader, though. Having strong faculty members on campus helps ensure that we have a strong group of students and postdocs that we can attract and further strong faculty members. Together, all of these impacts help ensure that our future alumni will have the education and experience they need to compete for the best jobs and to lead the nation and the world in maintaining and building scientific leadership. Francois, we're looking forward to great things. With that, I'd like to invite Dr. Jeff Schenker, Department of Mathematics Chair, up to the podium to say a few words on behalf of the department and to introduce today's honoree, Francois Greer.
All right. Good afternoon. I'm very happy to be here with all of you today to celebrate the investiture of Francois Greer as the inaugural Van Haften Endowed Professor in Deductive Literacy. Before I introduce Dr. Greer and his work, let me add my sincere thanks to Dr. Van Haften for his generous support for this position. The endowed professorship that he has so generously endowed aims to support deductive literacy in the modern world, bringing awareness of logical thinking to many disciplines. And now for a few words about our honoree. Professor Francois Greer received his PhD from Stanford in 2017 after distinguished postdoctoral positions at the Simon Center for Geometry and Physics at Stony Brook and the Institute for Advanced Study in Princeton. He joined the mathematics department at MSU in August of 2021. Francois is a leading young figure in the field of algebraic geometry. He studies enumerative algebraic geometry, modular forms, and Hodge theory. Now, you can be forgiven if you have no idea what I just said. These are deep topics at the cutting edge of modern mathematics. It is a peculiar characteristic of mathematics and mathematicians that we follow logical thought into seemingly obscure corners, illuminating new and fascinating ideas. At first, new mathematics is often abstract, logical poetry written in a language understood by only a few. However, built as it is on deductive reasoning, its truth endures, and its influence and application can grow over time. A 2,000-year-old treatise on geometry can lay the foundation for the rhetoric of a country lawyer and future president. Algebraic geometry follows in the tradition of ancient Greek geometry, medieval Persian and Arabic algebra, and European Enlightenment-era mathematics. It aims to study geometric objects by algebraic methods, that is, through the study of equations. Enumerative geometry counts the number of intersections between geometric objects. A simple idea. Two lines in the plane intersect in either 1 point or 0 points, if they are parallel. Modern algebraic geometry brings such studies to fields more abstract than classical plane geometry. Francois is an excellent mathematician and a well-rounded professor. His work in these cutting-edge fields is published in some of the top journals in mathematics. He is an engaged teacher, recognized by his students as being accessible and well-organized. He has directed an undergraduate research group and did a fabulous job co-organizing the department colloquium in 2021 to 2022. It is now my pleasure to invite Francois to tell us about the exciting mathematics he is discovering.
So where to begin? It's such an honor to be here. Thank you so much for everyone who took time out of their busy days and just to hear a little bit about geometry and algebra. So I hope you still have some gas in the tank for some mathematical thinking, because there's some Hodge theory and modular forms coming right up. So I wanted to start things off with a quote that I like quite a bit. It's similar to a quote that Dan will share with us later. I think it foreshadows the story that I'm going to tell. Michael Atiyah is a famous mathematician who recently passed away. He was a topologist, but I think a similar phenomenon was happening in topology in the past century as was happening in algebraic geometry. Okay, so what's the starting point? The starting point of my field is shapes. And in some sense, this is the most immediate experience of math that we all have. Like, we experience reality through shapes, and it's natural to try to create ideal versions of these things to understand their structure more clearly. And as mathematicians, we want to classify them. So can we make a list of all of them? Can we understand exactly how they fit together? Okay, so here's some nice pictures of shapes. So we all know, so Euclid started this whole story in ancient Greece, but he only considered shapes that could be constructed using straight edge and compass. So that restricts him a bit to straight lines and circles. And you can get a lot of things out of that, but not all things, as we'll see. So from my perspective, a big advance in sort of the types of shapes that we can classify happened when René Descartes introduced the coordinate axes. Right? So once you have axes, a point is really just a list of numbers. And it transforms the study of geometry into the study of algebra, or relations between these numbers. Okay, so a shape consists of a bunch of points, right? Often infinitely many points. So how can we make sense of infinitely many points? Well, a concise way to do that is to give a single equation, so a rule that the coordinates of those points have to satisfy. So I know a lot of people have seen these before, but so the first one is a circle, the second one is an ellipse, the third one is a hyperbola, and the last one is, I'll call it a cubic curve. It's a shape that's very important in modern number theory and algebraic geometry. So in the first example, the circle, I want to emphasize that we only keep track of the red line, so not the interior of the circle, just the edge of that circle. So that's the shape that I'm referring to when I talk about a circle. And here's a picture of the cubic curve, which is the last one. And here's a picture of the hyperbola. Okay, so you could just be done and say, I'm interested in all the possible shapes you can get from equations. But that would be a little bit lazy, because a lot of these shapes are actually the same in a certain sense. So if you change your perspective a little bit, a circle is actually the same thing as an ellipse if you just kind of look at the paper from the side. And the way we encode that mathematically is by a change of variables or a change of coordinates. So if you just replace y with 2y in the equation for the circle, you get an equation for the ellipse. So that might seem kind of obvious, but a less obvious one is that the hyperbola, which is on the previous screen, also is the same, in quotes, as the circle if we're willing to do a more exotic change of coordinates. So this change of coordinates might be hard to kind of think about, but if we go back to the picture of the hyperbola, the way I think about it is if you're sitting at the origin and you kind of circle your gaze around, you'll see exactly one point of the hyperbola in every direction, which is exactly what happens when you look around and look at a circle. So the change of perspective is by sitting yourself at the origin and kind of looking outward. Okay, so that kind of sets the stage for what is algebraic geometry all about. So we consider shapes that are defined by polynomial equations, which are essentially the simplest nonlinear type of equation that you could consider. So no sines, no cosines, no logarithms. This is good news for all the trigonometry struggle students. And the second assumption is I want to kind of view two shapes as being the same if they differ only by a change of coordinates, so a change of perspective. This essentially means that anytime we have a math problem about one shape, we can translate it into a math problem about the other shape and solve it there. So you don't really lose anything by changing coordinates. And the last assumption might be a little harder to swallow, is that I want to allow complex solutions to the equations. So complex numbers have a little bit of a bad reputation because they involve this imaginary number, but as we'll see, it actually simplifies our life quite a bit if we allow x and y to be complex numbers, not just real numbers. Okay, and so then just lastly, the reason that we use polynomial equations is that they make sense for any number system, actually. So the complex numbers, but also the integers or finite fields or other number systems that you might have heard of. Okay, so as an example, if you take this cubic curve, if you look at the complex numbers x and y, which satisfy that equation, instead of just the one-dimensional shape you have there, you actually get a two-dimensional shape, which is in yellow at the bottom. And you can recover the one-dimensional shape by just taking a slice of that two-dimensional shape. Okay, so looking at complex solutions kind of enriches the geometry of these curves. If you zoom out from this picture and look at the entire yellow surface, it changes color to blue, and it turns out to be a torus. And the other two examples, so the hyperbola and the circle, if you look at their complex solutions, believe it or not, they form a sphere. Okay, so you can take this a lot further and allow any number of variables that you want and any number of equations that you want. So just for simplicity, let's say that I have some algebraically independent equations in n variables, and there's k equations. So the shape that I should get will be an n-dimensional space, and the dimension of the space of the shape that you get will be the dimension of the number of variables minus the number of equations. Okay, but as we see, if we use the real numbers, this is sometimes not quite right. So the dimension can be smaller than expected. So for the first equation, you get a sphere, which is 2-dimensional. The second equation, you get a single point, which is 0-dimensional. And for the third equation, there are no solutions at all. So you have an empty shape. So another advantage of using the complex numbers is that the dimension of the shape is somehow always what you expect it to be. And so when you use the real numbers, there are extra points hiding that you don't see without going to the complex solutions. Okay, so a word about higher dimensions. Any kind of problem that has many variables has a certain higher dimensional geometry to it. So it's not, people like to ask, what is the fourth dimension or what is the fifth dimension? It just depends on what your problem is, basically. It could be the gas, the gas in your fuel tank. But it is harder to visualize shapes that are higher dimensional. But what you can do is you can take slices of them, or you can project them down to 3 dimensions, so you can have some intuition for what they look like. So here's an example of a shape that's very important for modern physics. It's a 6-dimensional shape if we look at the complex solutions. But if we take a slice of it and project it down to 3D, you get this shape which has a lot of singularities, so places where the shape crosses itself. Those singularities don't exist in the 6-dimensional picture, but with our kind of primitive eyes, we have to see these singularities. All right, so let's get back to the task. So we want to classify all the different shapes that appear when you take different equations. So maybe let's fix a dimension, and let's look at the degree of the polynomial. So how many variables appear in each term of the polynomial. As soon as the polynomial has more than 2 variables in each term, the solution shapes actually have continuous parameters. So if you change your polynomials around, you get truly different shapes. And this is kind of the starting point for moduli theory. So the big idea that I want to introduce today for understanding how these shapes can vary is what I call a force field, which for the mathematicians out there is an algebraic de Rham class. Okay, so a force field is kind of what you think it is. It's a description of a direction on your shape for every point. So this would be a picture of the torus, and there are these little red balls that are moving along the flow of the directions that are pointed out by this force field. And I want to require, since my shapes are defined by polynomials, that these force fields also be defined by polynomials. And this gets me to a finite dimensional space of force fields, which is very useful if you want to actually do computations. Okay, so a force field is, we'll say it's conservative, like, for example, the electromagnetic force field, if it's the gradient of some function. Oh boy, okay. So it looks like some things did not render in this version. Okay, well, lucky for you, there's no integral. So this is a very simple thing. Alpha equals integral of omega. So if you have a force field and you have some loop in your shape, you can do an integral. So you can basically integrate how much the movement along this loop is parallel to the force field. That gives you a number, alpha. Okay, and it turns out that these numbers are really powerful invariants of the shape. So they really tell you whether 2 shapes are the same. So if one of the loops can be deformed smoothly to another loop, it turns out that these characteristic numbers that you get are actually equal. Okay. Now I'm starting to worry about the math rendering for the rest of this talk. Okay, so all right. So if we take the set of all possible force fields and the set of all possible cycles on our shape, we can do all these integrals and we get a list of numbers that we can put into a matrix. If the shape is an even-dimensional shape, this matrix is an orthogonal matrix. If the shape is odd-dimensional, then the matrix is a symplectic matrix. And there's some change of coordinates that we have to worry about. So if we chose a different coordinate system for our force fields or a different coordinate system for our cycles. But once we take care of all that, the result is you get a parameter space for all the possibilities of these period numbers. And we call that D. It's called the period domain. It turns out that this period domain kind of holds a lot of information about telling two shapes apart. Okay, so a moduli space is a shape whose points correspond exactly to different polynomial shapes. So it's like we take the set of all possible shapes and we associate one point to each of them. And if two shapes are isomorphic, so they differ by a change of coordinates, then they correspond to the same point in the moduli space. So this is really the object that we're after, in some sense. And this process of taking integrals of force fields gives us a function from the moduli space, so this set of all shapes, to this period domain D mod gamma. So this is keeping track of what are the period numbers that you get out of these shapes. And the goal is to prove that this function is one-to-one. So in other words, if I know the period numbers, then I can recover the shape. And the idea is that this D mod gamma space is a bit easier to understand than the moduli space itself, because it just involves numbers, not shapes. So if we can somehow reduce the classification problem of shapes into something simpler, then we've somehow won. Okay, so just to give a concrete example, if you do the cubic curve case, it turns out that both the moduli space M and the period space D mod gamma are the same. And they can be identified with a single hyperbolic triangle in this Poincare disk. So strictly speaking, the D is the entire disk, and gamma is the set of all these hyperbolic triangles that tessellate the disk. And when you take this quotient D mod gamma, you're just essentially zooming on one of those triangles. So every point in that picture corresponds to a cubic curve of the form that we were looking at before. And you'll notice that, so first of all the triangles in this picture are isomorphic to each other, so they differ by a change of variables. And they all have a single vertex which goes and meets the edge of the disk. And so that, moving toward the edge of the world there for a cubic curve means that it's developing a singularity. You'll also notice that there are these darkened circles. There's one darkened circle on each of the triangles. And this corresponds to a very special cubic curve called the Gauss curve. And it's special because it has an additional symmetry. And that you can see that from the picture of the moduli space by the fact that you can reflect the triangle across that axis. Okay, so let's just kind of update ourselves on what's known about this approach to classifying shapes. So I think the original insight was by Abel. So he's the one who first thought about cubic curves in this way. So viewing them as their complex points and trying to understand, try to tell them apart using period integrals. So he showed that a smooth cubic curve is always determined by its period matrix. Going a step further, almost a century later, Torelli showed that actually this is not just special for cubic curves. You can do this for any curve. So a curve, remember, is just a one-dimensional shape. So it's a shape whose real solutions you can draw just with your pen. Fast forward another 60 years or so, and you have this theorem by Szafrewicz and Piasecki-Shapiro, which says that going up a dimension, any smooth surface can be determined by its period matrix. Okay, and then I just want to highlight a recent result, which will be posted this week with my two collaborators, Phil Engel and Abigail Ward. And it says that if you take a cubic surface, so this is a surface which is built out of cubic curves in the base and cubic curves in the fibers, is essentially determined by its period matrix. So there's a little bit of a caveat, which is that it's up to some finite ambiguity. We believe that this ambiguity is just 2. So if I know the periods, I can narrow down which surface it is up to 2 potential surfaces. And there's an interesting sort of reason what these partner surfaces actually, how they relate to each other. So that's one result. A much more desirable result would be the Hodge conjecture, which is a famous problem posed by William Hodge. What it essentially says is that if the period matrix of a certain shape satisfies some linear equation, then there's a polynomial shape inside of it, which is causing that linear equation to be satisfied. And this would be a very powerful thing to know. We don't know the answer. It seems to be true in every case that we can check. If it were true, it would be very, very powerful because it essentially reduces polynomial geometry, so the geometry of all these possible polynomial shapes, to linear algebra, to solving systems of linear equations. Okay, and it's known for dimension up to 3, but for dimension 4, it's wide open. So many people think that the key to approaching this conjecture is to understand what happens at the boundary of these moduli spaces and period spaces. So this boundary corresponds to, as I said before, when you deform your shape until it has a singularity, in the example of cubic curves. And we understand kind of what that looks like on the shape side pretty well, but it's still very mysterious what that looks like on the period side. So what does it mean for a period matrix to become singular? And so in some work in progress, I've come up with a way to at least give some partial completions of these period spaces. So in the case when the period spaces are not themselves polynomial shapes, it's tricky to kind of understand the boundary. And so I think I've sort of made the first step in that direction. But in some cases we're lucky, and this period space is actually a polynomial shape. So it is the solution of some polynomial equations. And in that case, it's actually quite easy to complete them, to understand what their boundaries look like. Okay, and so a natural question is, let's ask a meta question. So what are the period matrices of the period space? So it goes one step deeper. In a theorem by Borchardt, the period matrix of this space of periods, D mod gamma, can be determined by certain very famous sequences called modular forms. You might think that we're kind of stacking turtles on turtles here. Why are we trying to find the period space, period matrix of the space of period matrices? But in a lot of ways, I think it's actually more natural to study the period matrix of this. Because what it's basically telling you is, instead of telling you about a single shape, it's telling you about families of shapes. So if you have a family of shape that's deforming in a certain way, how many of the shapes in the family have a certain property? Those types of questions are the ones that are answerable by this technology. Okay, and so another recent result is that the period matrix, if you complete these period spaces, then the period matrix of the completion can be computed using slightly more exotic sequences called mock modular forms. And so both of these, I won't define these, but both of them were introduced by Ramanujan in the 19th century. Okay, so that brings me to the end of the math part. But first I'd like to extend a warm thanks to the Michigan State Math Department for welcoming me and for providing such a great environment. I really enjoyed, especially last semester, teaching Galois theory was probably the high point of my teaching career. I also want to thank my 3 RU students from last semester. Are any of them here today? Maybe not. Okay, Evan Bell, Pranjal Dongwal, and Minghao Zhao. I think Minghao, it would be hard for him to come. He's in China. But for their hard work, so what they did is they did a computer search to look for potential test cases of the Hodge conjecture. So they found a sequence of polynomial shapes which have the same periods. So if we believe the Hodge conjecture, then there should be some geometric reason for why their periods are matching up. I don't think that these Hodge coincidences, they're called, were previously known. And lastly, I want to thank Dan Van Haften for establishing this chair in deductive literacy. And more importantly, I want to thank Dan for showing me through his work that our way of mathematical reasoning has implications far beyond these polynomial shapes. I think to determine the truth and even more to convince others of that truth, deductive thought is an indispensable tool. Also, as I found out from Dan's work, is that some of the founding documents of our country are actually kind of modeled in the image of these Euclidean demonstrations. And we need strong arguments today more than ever before. So thanks very much.
Would you mind taking a question or two if there are any
yeah.
of the audience?
Your picture there, if you go to the Escher Museum, your picture of the hyperbolic, that's almost identical. Maybe you took it from. Was there any connection to what Escher was doing when he was drawing these curves in hyperbolic space to what you do?
Yeah, there is actually.
Was Escher working in Hodge there?
Yeah, it's actually kind of crazy. So the Escher shapes are what they call triangle groups.
Yeah.
Which are more, they're more important in sort of in dynamics and art, maybe, but miraculously a lot of these triangular groups are actually Hodge symmetry groups. So for instance, the one that I actually showed at the very beginning is an example of a period space for abelian surfaces. So the answer is that, yeah, it's a very happy kind of coincidence that these Escher shapes do come up.
I thought that's what he was doing.
Okay, thank you very much. Thanks, Francois, for that great presentation. I got through it and understood about a third of it. It's great. But I got to say, geometry is so interesting, and now I want to read a few more geometry books. It is now my pleasure to introduce the donor behind this prestigious endowed position, Dan Van Haften, who will provide the closing remarks for today's program. Dan is a 1970 alumnus of the College of Natural Science, where he earned both a bachelor's and master's degree in mathematics. After a very successful decades-long career in telecommunications, he retired in 2007 and started a brand new endeavor, studying the application of mathematical principles in thinking, writing, and argument. Just one day into his retirement, Dan found himself knee-deep in research at the local library on an unusual topic. He wanted to decode how an ancient Greek mathematical text had influenced Abraham Lincoln. Shortly thereafter, he tagged along on a trip to Springfield, Illinois, where Lincoln began his political career with lifelong friend David Hirsch, a practicing attorney who was to author a column for the American Bar Association Journal on Lincoln's legal practice. The two subsequently decided to write a book on the subject, and in 2010 published Abraham Lincoln and the Structure of Reason. Dan and David had since published 4 more titles, as our interim president just said, which you heard listed earlier, and have others in the works. It has been this work that inspired Dan to establish the Van Haften Endowed Professorship in Deductive Literacy in 2017, with the goal of planting a seed for connecting mathematical logic with writing across the university. With that, please join me in a warm welcome for Dan Van Haften.
Thank you, Dean Duxley. One of my goals today is to make certain that Phil understands 100% of what I say. Now, I gave a talk on behalf of donors at the September 14th University Investiture, and at that time I thought some people in the audience might be a little bit math phobic, so I didn't give the same talk that I'm going to give today. But today, Francois has inspired me to make a few changes in my talk. He talked about geometry and algebraic geometry, and I'm going to talk about geometry, but I'm not going to present a geometric proposition. I'm going to present a proposition about geometry. And I'm going to tell you about the 6 elements that I used to write this talk. The first element is the enunciation, and you start out with a given and a sought. So the given is basic facts. So let me give the given. It is an honor to address this investiture of Professor Francois Greer. The Van Haften Endowed Professorship in Deductive Literacy honors my parents, James and Esther Van Haften, who did so much for my sister Susan and for me. My father, my sister, and I are all Michigan State graduates. My mother graduated from Western State Teachers College, now Western Michigan University. She worked as a teacher to help put my father through Michigan State. We are all Spartans. Michigan State donors support outstanding professors, outstanding students, and outstanding programs. How did I become a donor? About 6 years ago, I met Samantha Adler from MSU Development at a Panera Bread in Batavia, Illinois. During our conversation, Samantha asked, "What can you do for Michigan State?" Her question made me think. So here's the SOT. The SOT is the second part of the enunciation, the first element. What can I give back to the school that gave me so much? Okay, now we're going to go forward to the exposition. The exposition presents factual information that sets the stage to bring the proposition forward. Giving by donors usually reflects their passions. Reasoning and geometry are among my passions. At a dinner with Keith Promislow, then the mathematics department chair, Keith asked rhetorically, "Is it more important that Michigan State freshmen know how to solve quadratic equations, or that they know how to think and write logically?" Keith answered his own question. It's more important that Michigan State freshmen know how to think and write logically. Keith's question made me think. Keith's answer made me act. At that instant, I decided to donate an endowed professorship to Michigan State's mathematics department. In 2007, I retired from a 37-year career at Bell Laboratories, AT&T, Lucent, Alcatel-Lucent, where I worked on telephone switching systems. When I retired, as Phil said, I began work on a book project with fellow Michigan State graduate David Hirsch, a friend from first grade, and now a Des Moines attorney. The 2010 book was about Abraham Lincoln. And Lincoln's passion for geometry rekindled my passion for geometry. 2,300 years ago, Euclid compiled what the Greeks knew about geometry. Abraham Lincoln studied Euclid to learn what it means to demonstrate. Our first book revealed what Lincoln learned when he studied Euclid. Lincoln used the 6 elements of a proposition to structure persuasive propositions in his speeches and letters from 1854 until his death in 1865. Euclidean propositions and Lincoln's writing method reason using the elements of a proposition. The 6 elements are the foundation of the scientific method. Approximately 1,500 years ago, Proclus preserved precise element definitions. Proclus's definitions are a lens into a Euclidean proposition structure. They became Lincoln's method for thinking and writing. Euclid and Lincoln worked with facts, words, ideas, and scientific reasoning. Okay, next is the specification. The specification is the hypothesis you're going to prove. The SOT is a very general statement, the specification, which was, what can I give back to Michigan State? The specification is a more precise statement of what you want to accomplish. So, one short sentence, but powerful. Geometry and the 6 elements of a proposition provide a method that leads to truth. So, that's what I have to prove. So, let's go forward. Next is the construction, where you marshal the evidence. It's factual. Keith Promislow suggested the term deductive literacy. Deductive because of the nature of geometric propositions. Literacy because it is a defined writing method that is reliable and enforces civility. Deductive literacy is the use of the elements of a proposition to verbally blend logic and fact in order to persuade. Abraham Lincoln applied the 6 elements of a proposition to human problems: slavery, civil war, and preservation of the Union. In the Gettysburg Address, Lincoln used the 6 elements to demonstrate what the North must do to win the Civil War and assure that this nation, under God, shall have a new birth of freedom. Thomas Jefferson also used this language of science as his method for persuasive resolution of human problems. Based on analysis of 19,000 letters and other documents written by Thomas Jefferson, my co-author David and I identified over 750 Jefferson letters and documents that demarcate into the 6 elements of a proposition. Jefferson used the 6 elements of a proposition in the Declaration of Independence, where he argued that these united colonies are and of right ought to be free and independent states. Jefferson's Virginia statute for religious freedom also demarcates into the 6 elements of a proposition. In 1821, Jefferson described writing the statute, quote, "The bill for establishing religious freedom, the principles of which had to a certain degree been enacted before, I had drawn in all that the latitude of reason and right. It still met with opposition, but with some mutilations in the preamble, it was finally passed, and a singular proposition proved that its protection of opinion was meant to be universal." So I've marshaled the evidence, presented some examples from Lincoln and Jefferson. So now we get to the 5th element, the proof. And the proof is where you argue. You've laid the foundation in the first 4 elements. So now you hopefully have established a basis for a solid argument. So here's the argument, the proof. The 6 elements were how Euclid, Jefferson, and Lincoln built propositions with structured facts and words that lead to iron logic and a solid conclusion. So yes, the elements can offer a civil method to equip Michigan State students to think, write, and persuade in the manner of Thomas Jefferson and Abraham Lincoln. When Thomas Jefferson used singular propositions to demonstrate fundamental principles, he helped establish the foundation for the United States. When Abraham Lincoln learned what it means to demonstrate, the elements helped him meet the major challenges of his day. I remember civil rights and anti-war demonstrations when I was at Michigan State. Present-day challenges are no less daunting. Some are new, some are similar, some are the same. But there is a new, old way to organize a demonstration, the 6 elements of a proposition. Thomas Jefferson wrote to John Adams in 1812, "I have given up newspapers in exchange for Tacitus and Thucydides, for Newton and Euclid, and I find myself much the happier." We can all relate to that. Why was Sir Isaac Newton one of Thomas Jefferson's favorite reads? Newton used a geometric rather than algebraic approach in writing the Principia, his work on the law of universal gravitation. So let me just say parenthetically, I'm going to introduce an argument from Sir Isaac Newton. He has more credibility than I do, so keep that in mind. In 1710, Newton wrote a preface for an unpublished version of the Principia. And you'd only run across this if you kind of read your way through the collected papers of Sir Isaac Newton, because this never got published. This 1710 edition didn't get published. This was in the preface. But here's what he said, and it's powerful. And it's the guts of my argument here. The ancient geometers investigated things sought through analysis, demonstrated them when found out through synthesis, and published them when demonstrated so that they might be received into geometry. Once analyzed, they were not straightaway received into geometry. There was need of their solution through composition of their demonstrations. For the force of geometry and its every merit lay in the utter certainty of its matters, and that certainty in its splendidly composed demonstrations. In this science, regard must be paid not only to the conciseness of writing, but also to the certainty of things. And on that account, I, in the following treatise, the Principia, synthetically demonstrated the propositions found out through analysis, end quote. 35 years before he wrote this summary of why he used a geometrical approach to the Principia, in 1675, Newton wrote, If I have seen further, it is by standing on ye shoulders of giants. Now the conclusion. The sixth and final element. And the conclusion is a logical progression from the sought to the hypothesis, the power of geometry, and the six elements to the conclusion. So, today we can stand on the shoulders of Euclid, Newton, Jefferson, and Lincoln. We need to do this. It is a joy to have Dr. Greer as the first Van Haften Endowed Professor in Deductive Literacy. He is wonderfully equipped to tackle the geometric challenges. He does stand on the shoulders of giants. But he alone cannot resolve all the challenges we face. It will take all of us. May deductive literacy prevail. Kinder and more gently, it searches for truth. Thank you very much. I can take questions if there's any questions.
Anybody like to ask any questions? If we read the local newspaper, I don't think we'd find any articles that satisfy these criteria.
Yeah.
Well, it was a wonderful talk. Thank you very much.
Thank you.
Thank you, Dan, for your inspiring and thought-provoking remarks, and I'll be thinking about them for a while. I won't say I understand 100% of that talk, because you might give me a quiz, and I don't want that. This concludes the formal part of our celebration today. We now invite you to join us to continue the celebration at the post-ceremony reception, which will be over there as soon as they open the doors. So thanks, everybody, for being here. It's been a wonderful event.
Good job. And there is, he loves the crowd, and so you could see him. I was watching; he was feeding off the.
To be able to see people.
Yeah, no, they didn't show because they want to.
But here, it's very different. Who wants to teach you that?
Oh, you did mention it. That's right.
That was part of the given.
Yeah, that's right.
I see. So that how many faculty in the department is that?
I know. We drummed up a few. I was messaging. I know. I could see you like they were so much like last night. Like I was coming in and every time like I sent them like a PDF.